All right, so number 2. All right, so let me rewrite this equation, y equals. All right, so let's find some ordered pairs. We know that whatever causes the parentheses to be 0 is going to be where your vertical asymptote is. Okay. Next up, we want to take advantage of this property here. If I have log base b of 1, that's always going to be equal to 0. So log of 1 is always 0. If I can find a way to get that to be 1, so I'm going to choose 3, because 3 minus 2 is 1. So if I choose 3, that will cause this whole expression to go to 0. All right, if I plug 3 in here, log base 3 of 1 is 0. So 0 times negative 3 is still 0. Next up, I want to take advantage of this property here. Log base b of b is equal to 1. If I can get the base and the value to match up, I can replace that whole expression with 1. So I'm going to take advantage of that property. I will choose 4, because 4 minus 2 is 2. If I do 4 minus 2 is 2, log base 2 of 2 is equal to 1. So this highlighted portion is 1, and 1 times negative 3 is negative 3. Okay, does that make sense?
I didn't know the second one, the second of the 4.
Yeah, so we have 3 properties. One is log of 0 is undefined, that's your asymptote. Log of 1 is 0, and the log base b of b is equal to 1. Okay, so I'll just work through the rest of this problem here. The parent function is just log base 2 of x. Transformations, we have 3 things going on. I'll list them out here. We have a reflection over the x-axis. I think a lot of students misinterpret the negative and the 3 to be one thing, but it's 2 separate things. The negative is its own thing, the 3 is its own thing. The 3 is going to be a vertical stretch. By a factor of 3. And the third one, that 2 is going to shift the graph to the right. Let's sketch the graph here. You got the vertical asymptote at 2. You have 3, 0. You have 4, negative 3. Okay, so normally the graph is rising, but that negative is flipping the graph over. Domain is from 2 to infinity. Range is all real numbers. Asymptote, x equals 2. Intercept, 3, 0. Now, if the intercept doesn't show up, then what you can do is you can set the function equal to 0 and then solve for x that way. A limit as x approaches infinity, that just means that if I follow the graph to the right, as I follow the graph to the right, basically I'm just following the path of the right arrow. as I follow the arrow to the right, what is happening to the y value? So this graph keeps dropping. So it goes down to negative infinity. The limits x approaches 2 from the right. That just means that we follow the left arrow as it heads towards this asymptote. As we get closer and closer towards 2, this y value is increasing up to positive infinity. So with limit, it's always asking for the behavior of the y value, behavior of the y value.
Will we have to use the log b 1 over b property on the test?
No, but I think it's good to know. Just to kind of highlight that property here, it shouldn't feel like completely out of left field. And the reason why this is -1 is because if I can get the bases to match, I can get the cancel out, right? So 1 over b, if I flip that b up to the top, the same thing as log base b of b to the -1.
Okay.
Right, and if I pull that -1 down in front, that goes away and that's equal to -1. So that's why it just gives us another order pair to line up our graph better, but it's not required. But I think it's good for us to understand why that's true. Okay, I'm just going to do one from each or a couple from each, and then you guys can let me know if there's any more that you would like to see. Okay, so highlight some problems from each section here. Rewrite each equation in log form. So log form, I know ultimately that means my exponent needs to be isolated by itself. So log base 4 of 1 over 64 is equal to -3. Okay. Number 6. Now I want to rewrite in exponential form. That means I want to get it into exponent form without the natural log there. So if it helps, I think it helps to rewrite your natural log as log base e to help you see the base a little bit more clearly. Because ln and log base e, they're the same thing. This is just a shorthand way of writing log base e. So now that this base is clearly seen, we can get into exponential form. E raised to the 2.303 is equal to 10. Okay, evaluate and pick some problems here. Natural log of e to the 5th. Now this is already in log form. So log form allows any exponent to come down in front. Exponent to come down in front. So 5 natural log of e, what is that equal to? Well, you know natural log of e is 1. So we know this piece goes to 1. 5 times 1 is just 5. Number 10, log base 10 of 10,000. Then we get it into exponential form. Get that base to show up, base 10. We can ask ourselves 10 raised to what power is equal to 100,000. You can either play with different x values to get that to be true, or you can rewrite 100,000 as 10 to a power. It's going to be 10 to the 5th power because of 5 zeros. So therefore, x must be equal to 5. I'll talk about this property here. This property says this: if I have a base raised to the log of the same base, then that just cancels out to just be 1, or just equal to whatever that value is. So in this case, 5 raised to log base 5 of 2, this whole thing, basically it's a function and its inverse inside one another. They're going to cancel each other out. The only thing left over is that 2. 14, log base 6 of 6. We want to take advantage of the fact that these bases are matching. This is in log form. Any exponent is free to come down. And log base 6 of 6 can cleanly go away to be 1. So 17 times 1 is 17. Number 15, I can rewrite this as equals to x, put it into exponent form. 8 to the x is equal to 16. I can use logs if I want, but looks like, I mean, these bases don't match yet, but I can bring them both down to a number that is shared. So 8 is 2 to the third power, and 16 is 2 to the fourth power. Now that the bases match, I can set them equal, set the exponents equal to each other. Twenty-seven and 9, I can play with both those bases to share the same one. So 1 over 27 is the same thing as 1 over 3 to the third. Keep playing with this here. This is still a little bit out of place. I can push that 3 to the top. This is really 3 to the negative 3. So 3 to the negative 3 with the x in front. So 3 to the negative 3x equals 3 squared. Drop the bases. Okay, here's 17 and 18. With 17, there's a hidden base, base 10. 10 raised to the x power equals 0.0001. I can play with that number here. That's really 1 over 10,000. And then 10,000 is really 10 to the fourth power. Bring that up to the top. Set the exponents equal to each other. And then same thing with 18. Get the bases to match. If I can show both of them to share the same base 7, I can drop the base 7 and set the exponents equal to each other. Okay, questions first page?
Does worksheet 4 have like all the stuff that we tested in?
Mm-hmm.
And it's like, we have to do graph,
Mm-hmm.
rewrite,
Mm-hmm.
evaluate,
Mm-hmm.
expand.
Expands, condense,
And that's all.
solve exponential equations, solve log equations. And, yeah, that's it. Okay, I'll pick the most challenging one. Well, if it's more challenging, it's just looks a little bit more involved here. So number 20, if I want to expand this fully, there's a couple options here. You can distribute that 4 through the parentheses first, or you can bring that 4 down in front and then expand and distribute the 4 through. It's really up to you, but I'll do it differently than the way I did with my key, so you can see the 2 different ways. Okay, so on my key, I brought the exponent down. I'll show you what it looks like if I were to distribute that exponent through. So when you distribute an exponent through, you're going to be multiplying. So there's really a hidden 1 here above that 200. So then 200 to the first power, 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12. We can expand using product property. And then the exponent can be free to come down in front. This is the way that I did it on my key here. I brought the 4 down in front expanded out, and then make sure the 4 tagged along to each term. And then that brought the exponents down. 4 times 2 is 8, 3 times 4 is 12. Okay, condensing. We want to try to bring all the exponents up first. Sorry, all the coefficients up first as exponents. So let me do 23 here. Natural log of b plus natural log of c to the third minus natural log of a to the second. Now I want to find a home for the b, the c cubed, and the a squared. And they're either going to live in the numerator or the denominator. So anything that's part of a positive or positive natural log or log is going to go in the numerator. Anything that's part of a negative natural log or log will go in the denominator. So b and c cubed will share the numerator. A squared will be in the denominator. Okay. So 1/2 minus distribute the 2 through 6 log m minus 8 log of n. I can bring those coefficients up. Now that 1/2 feels a little bit out of place because we see that these are both log base 10, right? We can definitely find a way to get that, but what do we do with that 1/2? Well, I can force the 1/2 to be something in the form of log base 10 because we know this is true, right? I can just force this to be log base 10 of 10 to the 1/2. Right, that's the same thing as 1/2 because log base 10 of 10 is just 1, and that 1/2 comes down in front. But if I write it this way, I can get everything to match with the same form. Now, I just need to find a home for the 10 to the 1/2, the m to the 6, and the n to the 8th. So log parentheses. The 10 to the 1/2 is the only term that is positive, so that's going to go in the numerator. All the negative terms will share the denominator space. Okay, next up, solving each equation. Typically, if something is in log form, we want to try to make our way to an exponent form. If something's in exponential form, so typically getting to log form, it can help us. So it's really good to just know how to go back and forth between the two forms. Sometimes one form can help us see the solution a little bit easier. Other times, another form is easier. So in this case, I want to solve for x, but x is stuck inside the log form. It's hard to see what's really going on there. This is really base 10. Get into exponent form, 10 to the 4th equals x. So now this is very clear, right? X is just 10 to the 4th, or 10,000. This is kind of cryptic. It's hard to see what's really happening here, but maybe exponent form can help us see things more clearly. My base is x, x to the 1/2 is equal to 3. Now I can just solve for x, right? What if I just square both sides? Then I can get that x by itself. One half times 2 is just 1. That goes away, so x is simply 9. Okay, 4 to the x equals 3. I want to solve for x, but x is stuck in the exponent. Typically, I would like to get the bases to match, but here 3 and 4 are not really compatible. So I'll just take the log of both sides. That frees up that x to come down. Divide both sides by log 4 to get x by itself.
So if you just have an exponent that's just kind of stuck up there, is it just best to put it in log form and bring it to coefficient?
That's what I would do, yeah. Unless the two bases are more compatible, then I would get them to share the same base. I can drop them out. So a good counter example would be 29. 29, you're free to take the log of both sides. Exponent can come down, but it may be a little faster to just work with the bases to get them to look alike. So 1/2 is same thing as 2 to the negative first power. 32 is same thing as 2 to the 5th power. In this case, it just feels easier to just get the bases to match and set the exponents equal. But if you were to go through logs, you'll get the same answer. Just take a little bit longer. Okay, 28 there. I want to solve for x. X is stuck inside natural log. I want to see what the base looks like. Log base e is same thing as natural log. Get an exponential form, e to the 1.8 equals x.
All right, appreciate Mr. Yang. I'll see you.
Yeah, I'll see you in class. Okay, so number 30, I can solve for x, but there's a lot of things that's messy there. So if I can just find a way to get this cleaned up. So bring the 3 over, drag the 4 to the other side as well. Now, careful here, we cannot multiply the 4 and 2 together. Okay, order of operation prevents us from multiplying because this exponent is unresolved. So that 4 is not with the 2. That 4 needs to move away from that 2. Right, so here the bases are not compatible, right? So here I do want to take the log of both sides so that exponent can be more easily dealt with. I'll just rewrite 3/4 is 0.75. The exponent comes down. If I can just divide both sides by log 2, I'll make it a little bit quicker for me to solve for x, I feel. So I'll divide both sides by log 2. Zero 0.195.
Well, what is that number on the right you got from?
This one here.
Yeah.
So I did log of 0.75 divided by log of 2 in the calculator,
Oh,
and that just gave me a decimal number there.
okay.
Okay, solving log equations here. I can combine some like terms first. This is in log form. I want to solve for x, get in exponential form. Solve for x, 32 minus 5. X is now, look at this here. This is a log equation, so we have to check for extraneous solutions. So that x plus 5 cannot be negative. 27 is not going to cause it to be negative, so we're safe. $32, I see that both sides are sharing base 10, log base 10, which is good. Typically, I like to find a way to get the logs to cancel out from both sides, but we can't do that just yet because there's some cleanup that's required here. So let's go through product property. Let's merge it into one log term, and then we can get them to go away. Get the logs to go away, log base 10. So log of A plus log of B equals log of A times B. Drop the logs now. X times X minus 2 is equal to 8. Now we can't do this. We can't say, oh, X equals 8, X minus 2 equals 8. This doesn't work unless there's a 0 showing here. So we have to bring everything over to one side, get that 0 to show up, and then factor, and then solve for X. So we can't set this equal to any number other than 0. Multiplies to be negative 8, adds it to be negative 2, negative 4, 2. So X is 4, and X is negative 2. But remember, we have to test against our original equation. Make sure it doesn't cause any of those expressions to be negative. 4 should be safe. 4 doesn't cause any issues. 4 minus 2 doesn't cause any issues. But negative 2, if it causes even one thing to be troublesome, we have to remove it. So negative 2 doesn't work for either. But if it worked, even if it fails for one of them, it's not good enough. It's got to pass every single one. It doesn't do that. So this is my extraneous solution here. Only 4 works. Okay, 33. I would like to work with the exponents, maybe involve logs, but right now there's too many terms here. But I can merge them together here because I have if I have bases that are being multiplied, a to the m times a to the n, I can merge it together by adding exponents. So I can combine those 7s together and then just add the exponents. Okay. 7 and 14 are not quite compatible from a base perspective, so we have to take log of both sides here. Bring that exponent down. Okay, let's bring that log 7 over, divide both sides by log 7. Log 14 divided by log 7. Is 1.356. Subtract 2 from both sides. Oops, sorry, negative 0.643. Divide both sides by 2.
You just do the first graphing problem.
Mm-hmm.
Don't do the little limits.
Okay, so we focus our attention on the expression inside the parentheses. That's where you're going to find your vertical asymptote. Set that equal to 0. X is negative 4. That's my vertical asymptote. I want to take advantage of this first property here, log base b of 1 equals 0. If I can choose an x value strategically here, I'll choose negative 3, because negative 3 plus 4 is 1. Log of 1 is 0. 0 minus 1 is negative 1. Okay, another strategic x value for us to choose is to find a value that will match the base. So I will choose negative 1, because negative 1 plus 4 is 3. Log base 3 of 3 is 1. And then 1 minus 1 is 0. Okay, parent function is just that log base 3 of x. Transformation, there's only two things here. Shifting left 4 units and down 1. Domain, it's from that asymptote to the right, so from negative 4 to infinity. Range, all real numbers. Asymptote, there's vertical asymptote at x equals negative 4. X-intercept, negative 1, 0. Again, if the intercept doesn't show up for you, you can just replace your y with 0 and then just solve this log equation. Limit as x approaches infinity. So again, this means follow the arrow to the right. So here, this means as I move to the right, as my x values increase, what's happening to my y value? So this arrow is steadily moving up. So it's going up to positive infinity. As we approach 2 from the right, that means we're approaching the asymptote. What's happening to the graph as it approaches the asymptote? We're going to follow the left arrow. The left arrow is going down. So it's going down to negative infinity. Okay. Any other ones you want to go over?
What?
Any other ones you want to go over?
Um. 36.
Okay, so this is stuck in log form. I want to solve for x. So let's get into exponential form. So 3 to the 4th is 81. Divide both sides by 16. X equals 5. But there's one more thing we got to make sure of. This is a log equation to begin with, so it has to not conflict with that expression. It's got to produce a positive value. If I were to plug in 5 in for x is safe, this will give me a positive value. So we've confirmed this is our valid solution.
So even if the x is negative, if all the equations from the top like make it positive, if you plug them in, it'll still.
It still works, yeah. So just because it's a negative value, it doesn't ensure it's gonna always fail. Likewise, just because it's a positive number doesn't confirm that it's always gonna be that's gonna be part of the solution. Okay, so you gotta make sure you insert and double check for every potential solution.
Thank you.
All right, see you guys.
Is Monday like a normal school day or is it a recovery day?
I think technically it's like a quote unquote normal school day, but I think we're required to take attendance, but really it's meant for the teachers to have a day to grade and see if there's any, upload their grades, make sure that there's no failures or any students who need recovery, and then let students know, hey, you can come in Tuesday, Thursday, but yeah, it's kind of like it's not really defined very well, but I mean, I hope to have all the grades in by Sunday. And so, you can show up on Monday, but I may have to still take attendance. So, okay. All right. See you in class.
Thanks.